Hey, hello and welcome back everyone. We're moving on to really a subsection of the previous one where I introduced the total derivative, multivariable functions. Today we're working with the directional derivatives and in particular the gradient or the gradient vector. It turns out the gradient will be represented as a vector. So for this section we are really going to be focusing on multidimensional functions that only take a single dimensional output or a single dimensional value. In other words, I have an f with, as many inputs as I would like, but a single output. And often these functions are called scalar fields. Scalar because the output of the function is a collection of scalar values, right? You can scale vectors by real numbers. Okay, so these are called scalar fields, and we're going to be looking at really the derivative, but what we eventually want to accomplish out of this is the directional derivative. We're going to take the derivative, which we experienced in the last video. Total derivative is the matrix, but in this case, because we have n inputs and one output, this is a 1 by n matrix. Okay, so just a single row of a matrix, and in each entry of the matrix, we have the partial derivatives of the function at hand. And let's recall what the total derivative is actually trying to represent. It represents a multidimensional linear map, in this case, also from Rn to R. And we can think about this linear map as named L, so we're going to give it the name L. It has itself n inputs. And if we act, basically we consider this as a matrix acting on a vector, the vector of inputs. That's really what we have here. Matrix acting on a vector of inputs. What do we get out of it? Well, you get the partial derivative in the first variable times the first input. You get the partial derivative in the second variable times the second input, and so on. The partial derivative in the nth variable times the last input, and you add all of those together. So in condensed notation, this linear map, the total derivative has its own input, which we think of as the point in the domain of f, right? So this is the point we're kind of finding the derivative at. And then there's this second input, which is really the input to the linear map. The second input we think of a direction. Okay, so there's a directional input here, a direction in which the slope will be computed. And this word slope here is unique. Well, once I give it a direction, it's unique in the sense that, right, regularly slope will always be rise divided by run. Well, because we only have a single output here, there's only a single direction you can rise in. And there might be multiple directions to run in, but that run is the entire point of this y. So we're looking for the rise over the run. The run happens in the direction of this y input. And we're looking for the rise over the run at a specific input to the function, a specific point in the domain. That's what that x is referring to. So it's the rise over the run in the direction of y located at the space x. That's really what this linear map, which is the same thing as the total derivative, that's really what that linear map is trying to compute for us. And so here I've got a little graphic. You can imagine here is my function f of x and y, and of course I've kind of assigned that to be the z variable here. So the height is the output of f of x, y. And then in particular, this point, let's call it x0, y0, is the point right here that I'm going to evaluate a derivative at. Okay, so that's some point in the domain, right? That's a point in the xy plane. And then in particular, I'm also asking about, I'm giving myself a direction. So there's a direction in which to compute the slope. And if I give this direction a vector representation, let's say it's the vector representation a, b, right? So maybe the direction of this vector is the vector a, b, then I can compute the slope with, well, you take the derivative, you evaluate the derivative at this special point in the domain, but then you act the derivative on the vector which is pointing in the direction we care about. So that's going to turn out to be the idea of the directional derivative, right? Because it's a derivative specifically in a direction. Now let's point out that vectors have more than directions involved with them. They're both magnitudes and directions. And so to be particular about directional derivatives, we do actually require that the direction vector is a unit vector. Okay, so here's what we saw earlier, right? There was this derivative, df, evaluated on an input x, and then it was acting on a specific vector that was the direction we cared about. But earlier we weren't really specifying that it had to be a unit vector. In fact, we do need to specify that it's a unit vector because if it weren't a unit vector, it would involve both a magnitude and a direction. In some sense, the magnitude being exactly 1 is the most trivial magnitude. And of course, most trivial non-zero magnitude, because a vector that has magnitude 0 really isn't a vector, right? So this one still has a direction, but it's got kind of the most trivial magnitude we can assign to it. And so if I scroll back up really quick, we do require that this arrow, we require the direction vector to be normal or normalized. So this goes all the way back to why would we ever care about normalizing vectors? Well, here's one of the reasons we care about normalizing a vector. Is that to define a directional derivative, we really only care about its direction, not its magnitude. So we're going to divide it by its magnitude and make sure the norm is equal to 1. Then we can use it as our directional derivative. We have a different notation for the directional derivative. Often it's notated with this upside down triangle. This the symbol is called nabla. I know it's kind of a weird word to say, nabla. We give it a subscript in the direction vector. And if you think about what would the output of this action be, and I've kind of already described it, well, the output of that action is exactly this summation you see here. We take each partial derivative in the I direction of our function, and we multiply that by the I component of this unit vector u, and then we add all of those terms together. But what that means is that this will be a single real number output, which describes the slope on the surface if traveling in the direction u. You get a single real number that describes the slope. If I jump back up here, you can imagine if I'm physically walking on this mountain in this direction, there will be a very specific slope of the mountain in that direction. The directional derivative was constructed as a means of saying, how do we calculate that slope? Let's go ahead and compute it. Here we have a scalar field, which recall just means a function with a one-dimensional output. This scalar field is x squared, y squared plus 3xy. And we're going to compute the directional derivative. We need two pieces of information to compute the directional derivative, right? We need the location at which I stand. And we also need the direction in which I walk. Once we have those two pieces of information, as well as, I guess you could interpret this as the shape of the mountain. So there's the shape of the mountain, there's the location at which I stand, and there's the direction in which I walk. All of these are required for me to gain a directional derivative, in other words, to gain some notion of a slope in the direction I'm walking. And once we have those three pieces of information, we can actually compute it. So how are we going to compute this? Well, we're simply going to compute the derivative of this function. Well, let's recall how to take the derivative of this function. We go ahead, we've got it here. It's the partial derivative of x as the first input to the matrix, and then the partial derivative of y in the second input of the matrix. So if we take the partial derivative of x, that's going to give me a 2x on that term with y squared coming along for the ride, and it's going to turn 3x into 3. So we'll end up with 2x y squared plus 3y. If I take the directional derivative, the direction of y, well, it's going to give me a 2y right there with x squared coming along for the ride. It's going to turn 3y into 3, and the x is going to come along for the ride, so I'll have 2x squared y plus a 3x. So we've computed the derivative, and now we're going to have to say, what is the derivative specifically at a point? In this case, the point is 1, 1. So we're going to go ahead and evaluate that derivative. Derivative where I stand. So we'll evaluate the derivative exactly where I stand. That's what I've done here. I've evaluated it at the point 1, 1. And it looks like the output will end up being 5 for the first output and 5 for the second output. that's going to be a matrix, right? So the full derivative evaluated at a point will just give me a matrix. It'll give me a single row of a matrix, but it is a matrix. So in this case, the matrix is 5, 5. And then this whole time, the direction that I've cared about u has kind of been sitting around, not doing much until I evaluate my matrix. But once I evaluate my matrix, it looks like I've got a matrix acting on a vector. We all know that a row matrix acting on a column vector will just give a single output. So we're going to get a single output out of this. It's basically the same as the dot product now. You can think about this as a quote-unquote dot product. If you like to think about both of them as vectors, quote-unquote dot product, we're going to take 5 times 3/5 plus 5 times negative 4/5. So you can give us 3 minus 4. Turns out the directional derivative of this particular mountain, whatever you want to call it, surface, located at the point 1, 1 in the direction of 3/5, negative 4/5 happens to be negative 1. We'll do one more example in 3 dimensions maybe. Right, so we can change the number of dimensions of the input as much as we want. It's just this output needs to always be one-dimensional. That's what makes it a surface. It's a higher dimensional surface in other cases. You can't really graph it as a surface, but it is a surface. And so it still has slopes in every direction. And in this case, I've given myself the function g of x, y, and z is the sine of x plus the cosine of y plus z. And I would like to find the directional derivative if I'm standing at the point pi over 4, 3 pi over 4, 5 pi over 4. And not only do I have to stand somewhere, but I also have to walk somewhere. And which direction am I walking in? I'm walking in the direction of 1, negative 1, 0. Now it turns out in this case, we do have an extra piece of work we have to go through, because if we check really quick, what is the magnitude of this vector v? Well, we get the square root of 1 squared plus negative 1 squared plus 0 squared. We see that the magnitude of v is the square root of 2, which means it's not a unit vector. No worries if it's not a unit vector, we can convert it into a unit vector. But to get the directional derivative, we will need a unit vector, not just any vector as our input. So we'll have to go through a little bit of work to convert this to a unit vector. The fact that we have this square root of 2 is really all we need. We're just going to go ahead and divide this vector v by its magnitude, which is the square root of 2. And so here I've gone ahead and divided it by its magnitude. I'm just going to pass that magnitude 1 over root 2 to every entry. And so the unit vector, which describes the direction of v, is 1 over root 2, negative 1 over root 2, and 0. And so this is the vector we'll end up using for the directional derivative. Now with the directional derivative, we'll also actually need to compute the total derivative of g, and we'll still have to evaluate at the point that I'm standing. So we're going to go through that work. If I take the total derivative of g, that's going to be partial x as the first entry in my matrix, partial y as the second entry, and partial z as the third entry of my matrix. And what I'll get out of that is a cosine x in the x direction, a negative sine y in the y direction, and a 1 in the z direction. And I'll have to go ahead and finish out by actually evaluating at the point at which I stand. Otherwise, this doesn't make any sense. So we're going to evaluate where I'm standing. That's going to plug a pi over 4 in for x, 3 pi over 4 in for y, and a 1 in for z, which will evaluate cosine pi over 4 is 1 over root 2, negative sine of 3 pi over 4 is negative 1 over root 2, and of course z doesn't really have any terms, so that's just going to stay equal to 1. And then as always, this is a matrix acting on a vector, but a row matrix on a column vector, we're just going to get a single output. You can think about it as a dot product if you'd like. We have 1 over root 2 times 1 over root 2, so 1 over root 2 squared, or 1/2. We have negative 1 over root 2 times negative 1 over root 2, negative 1 over root 2 squared, also 1/2. We have a 1 times a 0, which is a 0. Turns out the directional derivative of our function at this particular point in the direction of v is equal to 1. So it turns out that this idea of the directional derivative is quite useful. You can talk about derivatives in any direction of some sort of surface if you were standing at a point looking in any direction. Now there's one very, very special direction, and that direction is the gradient, or often the gradient vector, because as a vector, it describes the direction of steepest ascent. You can imagine if you're hiking a mountain, no matter where you're standing, there's going to be, at least locally, right? It might not be the direction up to the top of the mountain at any point in time, but locally, there's going to be a direction for which you would have to step the highest to step forwards. And that is a very unique thing, right? And so it turns out that that very special direction, which is the direction of steepest ascent, gains a very special name. The name is the gradient. And this makes a little bit of sense. If you're talking about the gradient of a hike, you would be talking about kind of the slope at which you're hiking at any point in time. But we reserve this for specifically the direction that's the steepest slope. And so it has this kind of really nasty definition that involves both the max and the argmax. So max meaning it's the maximum value that the directional derivative can obtain. That's what we're saying here. It's the max value directional derivative can obtain. But we also care with the argmax because the gradient is a vector. Not only does it obtain this maximum value, and we actually normalize it with a 1/2 that's serving the role of the square root inside of a magnitude, but we take that maximum value and we're actually going to multiply it by the direction which actualizes that maximum. Now here I said at the top that the gradient describes the direction of steepest ascent. That's true, and you could arguably just get away with it only using this later term, the argmax of the directional derivative, arg meaning the argument of the maximum of the directional derivative, like the input. It turns out there's natural reasons that we want to multiply kind of by the square root of the maximum value, and we'll see below what that reason is. So just take it for granted now that we're going to multiply that arg maximum, the actual direction of steepest ascent, we're going to multiply it by the square root of what the maximum value actually is. Because when we do that in this proposition, it makes it a lot easier to compute the gradient vector. It turns out that there's a very, very easy way to compute it if we just go ahead and multiply by the square root of the maximum value that's actually achieved. And the way you compute it is you just have the vector of partial derivatives. It's nothing more complicated than the vector of partial derivatives. Or if you recall that the derivative, the total derivative, is a row matrix, if you use this operation, which is called the transpose, and I've mentioned it a couple times before, this swaps all rows for columns. Well, if you start with a row matrix and you swap a row for a column, you're now getting a column matrix. If you turn around and actually interpret the column matrix, even though these are slightly different things, if you interpret the column matrix as a vector, you exactly get the gradient vector. And it turns out that this thing always points in the direction of steepest ascent. And so that's extremely useful that this vector, which is very easy to compute, necessarily points in the direction of steepest ascent. Very useful concept in multivariable calculus. Got a nice proof there that actually shows that it is the direction of steepest ascent. We're going to skip over that. We're going to talk about this remark. So this remark is something that really shows up a lot especially in physics, but quite a bit in mathematics as well. Which is that, while we technically just defined the action of this nabla object on F, we technically define the action of that on F, always acting on a function as the vector. It's actually extremely notationally convenient to think about the symbol. Remember, this is the symbol called nabla, but now it's going to make sense why sometimes people will refer to this as grad. Okay, so you can call that symbol nabla or grad, or even del. Some people call it del, kind of like delta. It's an upside down delta, right? So you call the symbol nabla or grad or del, but you can represent the symbol as a vector of partial derivatives, right? It doesn't really need a function as its argument. You just start to represent it as a vector itself, where the entries in the vector are partial derivative operators. And what that allows you to do, especially for the physicists, is construct some notations like this, where you're taking the dot product of nabla with a vector field, or some function whose outputs are vectors, or maybe you're taking the cross product of this vector nabla with a three-dimensional vector field. So we're going to see those really quite soon show up, and it's a useful notation. So you can think about this nabla or gradient or whatever you're going to call it as the vector of partial derivative operators. So let's go ahead and just compute the gradient a few times. It's really quite straightforward if you manage to get through the last video where we were talking about the total derivative. It's, as I keep saying, it's the vector of partial derivatives. So if we've got a scalar field here, which in my case is sine of x squared plus y cosine z, we're just going to compute the vector of partial derivatives, partial x of this, which happens to be 2x cosine x squared plus y cosine z. I'm going to take partial y of this, which happens to be cosine z times cosine of x squared plus y cosine z, or I'll take the partial derivative in z direction of this, which happens to be negative sine z times cosine of x squared plus y cosine z. And so you just get this nice big vector out of the gradient, right? So we call this the gradient vector. And I can't stress this enough, points in the direction of steepest ascent. Let's look at another example, this one in 2 dimensions. So there are 2 inputs, x and y, which means that our gradient vector will only have two rows or two entries, it'll have partial x and partial y. In this case, if I take partial x of x over 1 plus y squared, I will get 1 over 1 plus y squared. If I take partial y of x over 1 plus y squared, I will get negative 2xy over 1 plus y squared squared. And then finally, I've provided an example where technically you can call the gradient the same thing as the derivative in one dimension, right? So if I take a one-dimensional function, x squared minus 2x plus 2, and I compute the gradient, this is technically the vector with a single input, and then the output will just be the derivative in the x variable, in this case 2x minus 2. This always points in the direction of steepest ascent. I hope you can believe me why. So let's take just an arbitrary function here. There's my arbitrary function. If I'm standing somewhere that the derivative happens to be negative, right? If my slope is negative, that means that this output would be negative, which means that the negative direction, so negative direction is steepest ascent, right? So which direction should I walk in to ascend the quickest? If I'm standing here, well, I want to walk in the negative direction to ascend the quickest. And of course, the opposite is true when the derivative is positive, because you're walking uphill in the positive direction then. So yeah, this definitely works in one dimension. Of course, it's a lot more powerful in higher dimensions to find out that direction, which is going to maximize the next step you take. So after we have the gradient, we can actually compute the directional derivative in a second manner, right? And this is really showing us why we use that notation nabla sub u, because if we compute, remember how I said when we were computing these, it's a lot of, it behaves a lot like a dot product. Now this is a true dot product. If you would rather interpret the directional derivative as the gradient, which is now a vector, not a matrix, right? The derivative, the total derivative of a function is a matrix, but the gradient is a vector. So now you take a vector and you dot product with the unit vector you would like to check for the directional derivative in. And so that's just a slightly, maybe it's easier. This is maybe a more common way that a lot of people interpret computing the directional derivative as a dot product with the gradient rather than the action of the derivative on the unit vector that you're looking at. Well, one more main takeaway. The primary moral of this subsection, and the idea that many future courses will expect you to remember, is, and I'm going to say it again, the gradient of a scalar value function points in the direction of steepest ascent. So please do not forget this. Everybody is going to expect you to remember. There's like 3 things you're expected to remember out of multivariable calculus. This is absolutely one of them. The gradient vector points in the direction of steepest ascent. And it's also very easy to compute. It's the vector of partial derivatives. And so that object is actually really easy to compute. And it's a useful object because you want to know which direction to walk in to maximize your next step. And I mean, why do you want to know this outside of a mathematics course? This is how you computationally optimize a lot of problems. So if you're running any sort of code and you would like to optimize, you calculate the gradient of wherever you're located, wherever the code is looking at, and you can kind of locally calculate the gradient and then choose another step to move in. So if you're optimizing a lot of things, and we're going to encounter optimization in this course too, but really higher dimensional optimization, something called gradient ascent for maximizing, and gradient descent for minimizing is super popular. Anyway, here's a lovely picture of specifically the gradient at this point. You can tell it's pointing straight up the mountain. So that is what I would like you to remember. I think we've got a little bit of time. We can at least get the next section started a little bit. Sections on higher order derivatives and the Taylor series. We're just going to accomplish higher order derivatives here, basically because it's a pretty straightforward topic. You would expect, right? The answer is yes. Can we compute higher order derivatives by repeating the derivative operation? Of course you can. So you just repeat the derivative operation exactly like you might expect. The way that we do it is we have to be a little bit careful with our notation, right? Because if our notation takes f, which is multi-valued, and then you take the derivative d and you get df, which is now a matrix, also multi-valued, the next derivative, what does that send you to? Well, d squared f is going to send you to a matrix of a matrix. Okay, and in reality, these objects, matrices of matrices, these are called tensors. We're not really going to get into their definition in this course, but these higher order derivatives are these mathematical objects called tensors. And you can think about tensors as matrices of matrices. And you can iterate that as much as you want, of course. So you get to some slightly complicated things here. It ends up being easier computationally than it looks. And also notationally, like it's not too hard to embed a matrix inside of a matrix. And of course, what do I have as my definition here? It's the definition you'd expect. It's simply, I'm computing the derivative right? The kth derivative is going to be one extra round of a matrix of partial derivatives, right? A matrix where each column is a new partial derivative input, just like the other derivative that we originally learned. And you're going to act those partial derivatives on the lower order derivative, right? This is there's a slight typo here. We're missing d to the k minus 1 there. But you're just acting the derivative on the previous derivative and interpreting it now as a matrix of matrices rather than like just a matrix by itself. So let's go ahead and compute this and see how the matrix of matrices looks. Here's my function f, and it has two inputs, x and y. It's got two outputs, x, y, and negative y squared. If I want to compute the first derivative, right, the first derivative just takes the output, which is a vector at this point, and it computes the partial derivative in the x direction and the partial derivative in the y direction of the entire vector. And so the derivative in the x direction distributes, the derivative in the y direction distributes. We have x on xy, which gives me y. We have x on negative y squared, which gives me 0. We have y on xy, which gives me x. And we have y on negative y squared, which gives me negative 2y. And so I guess you could interpret this as a matrix of vectors if you would like to, but we often, and I think you have done so far, we do often just drop the inside parentheses, and now we just have a single matrix, which is a 2 by 2 matrix, and that's how we interpret the derivative, right? It's a 2 by 2 matrix because we have two inputs and two outputs. Totally fine for the first derivative, you've been practicing that before, but now simply for higher order derivatives, we're going to grab this object and we're going to take a derivative of that object, which means we have a new matrix with new partial derivatives, and we just directly translate the object we would like to take derivatives of inside of that matrix with new partial derivatives. So now we've got partial x on yx 0, negative 2y, and partial y on yx 0, negative 2y. And of course, just like before, we're going to take this and distribute to every single term in the matrix. We're going to take this, distribute to every single term in the matrix. And what do we get when we distribute partial x to each entry? Well, we get the matrix 0, 1, 0, 0. And if we distribute partial y to each entry, we get 1, 0, 0, negative 2. And of course, at this stage, you could see, note, if we took another derivative, we would get all zeros, right? We get all zeros because all these entries here are just constants, and so everything would turn into zeros. We'd have an even bigger matrix, right? It's a matrix of a matrix of a matrix at that stage, but everything would be 0 on the inside, which will start to make a lot of sense. Why should everything be 0 on the inside? Look at these. What is the total power of the terms? These are really both quadratic functions. Quadratic, or total power 2 functions. And what do we know about taking 3 derivatives of quadratic functions is that they should turn into 0, right? 3 derivatives of x squared becomes 0. And so we start to see that actually higher dimensional functions kind of occupy a similar intuitive sense that after taking enough derivatives of polynomials, everything turns into 0. But we do have to play this nasty game of putting matrices instead of matrices, which is a little bit frustrating. Also kind of fun. This last step, I do mention, I guess you could, if you want to, drop the parentheses here, just like how we dropped the parentheses when we took the first derivative. But in this case, you really need to interpret every single time you put these parentheses down, you're gaining a dimension. And so the fact that there are 2 sets of parentheses here, and there's a 2-dimensional object on the inside means that there's really 3 dimensions worth of space happening here. And so to drop the parentheses and properly notate everything, you kind of write it as this 3-dimensional, this is still called a tensor, right? Tensor or tensor array. So it's a three-dimensional array in this case. I hope you think it's pretty though. It took me a long time to type the code to make that work. We can do one other case of a second derivative computation. In this case, we are going to take the second derivative of a scalar field. And of course, the first derivative is the row matrix where each column in the matrix is a different partial derivative of our function. So I take a partial derivative in the x variable of x cubed y squared z, where you can get 3x squared y squared z. I take a partial derivative in the y variable of x cubed y squared z, we're going to get 2x cubed y z. If I take a partial derivative in the z variable of x cubed y squared z, we're going to get x cubed y squared. And so this is going to be the first derivative, which means things get pretty ugly on a second derivative in terms of width. Right, if I'm going to take a second derivative of this object, if I take d, this object here, that's going to be the row matrix where each entry, each row, is partial x, partial y, and partial z of the previous input. Right, this is this entire term. So what goes into each of those partials is going to be a 1/3 matrix. And so that's a 1/3 matrix, that's a 1/3 matrix, that's a 1/3 matrix. We're going to end up with a 1/9 matrix. It's a very wide matrix. But we can do it, and to save some space, I've kind of done it, but I have kind of hinted at the fact that we might want to start putting this in a matrix form. So I've kind of hinted at that fact here. I think you can kind of see it. So here's partial x of the input, partial y of the input, partial z of the input, and to be perfectly pedantic, that should go there, and that should go there, and we'd have a 1/9 matrix. But I don't do that here, and instead I've kind of started to put them over top of one another. I'm still going to distribute partial x, partial y, and partial z to each of the inputs. And when I do that, I do recover, 9 total terms, which I've somewhat placed underneath each other. And really, they should be adjacent to each other in one long term. But it does behoove us to put these in a matrix. And so how does this work out? It turns out when the output of the original is one-dimensional, then the second derivative of f can be represented as a matrix. And it's just going to make your life prettier if you decide to represent it as a matrix. Now, that's only going to work if that original output was one-dimensional. We learned earlier today, those are called scalar fields. But how does that look? Well, here I've done it with that previous problem, where now I've taken this first row we think of as the partial x squared, partial x, partial y, and then partial x, partial z entries, and then they continue to partial y, partial x, partial y squared, and then partial y, partial z, and then finally partial z, partial x, partial z, partial y, and partial z squared. Right? This is all combinations of second derivatives. All combinations. And now they're in a matrix where all of the terms are a little bit more neatly oriented. Turns out that matrix has a lovely name. It's called the Hessian matrix. And so we do have our own special word for the second derivative of scalar valued functions, right? Scalar valued or functions with a single output. Functions with one-dimensional output. If I take two derivatives of that function, I can represent them as a matrix. And that's what I say here, rather than a 1 times n tensor. What do we need that one row for? Basically nothing. And so we just think about the n times n tensor now as a n times n matrix. And it just condenses notation for us. Very nice. Also talk about something called Schwarz's or Clairaut's theorem. This is just a nice theorem that I would have had to bring up eventually at some point in higher order derivatives of multivariable calculus. People use this all the time. What does this theorem say? It says if a function, multivariable function, is 2 times continuously differentiable, this means that all second derivatives are continuous functions. Nice thing being that like polynomials, trigonometric functions, exponential functions, they all satisfy this. So if all second derivatives are continuous functions, then you can freely exchange the order of repeated partial derivatives. So that means partial xi, partial xj is the same as partial xj, partial xi. Or maybe to make it a little clearer, if I do it in the variables x and the variable y of some function, this is the same as the variable y and then the variable x of some function. What does this mean in terms of the second derivative matrix that we just encountered, the Hessian matrix? You can start to see it. If I look at this entry and I look at this entry, they must be the same. Similarly, if I look at this entry and this entry, they must be the same. Similarly, if I look at this entry and this entry, they must be the same. You've taken linear algebra and you talked about symmetric matrices. Clairaut's theorem or Schwarz's theorem says that the Hessian is always a symmetric matrix when your function's twice continuously differentiable. Right, symmetric in the sense, if I draw that line, you can flip over the line and everything stays the same. So that saves you some computational power. That's kind of the point of this theorem. You start to see that you don't need, if you're taking the kth derivative of a function, instead of needing n to the k computations, you need something called the nth k simplex number. That's something fun to look up, the k simplex numbers. Triangle numbers, if you've heard of those, are one example of simplex numbers. Anyway, I do have one example of the Hessian matrix computation. It's exactly the same as the second derivative computation. I guess I forgot to mention the Hessian matrix can also be notated as nabla squared, right? We encountered the nabla notation today. You can also do nabla squared as the kind of the second gradient, right? The second gradient and the Hessian are the same. So I do mention this here. Hessian can also be d squared or nabla squared. I'm going to try to stick to lowercase d squared, but periodically you may see me use nabla squared for the Hessian. So this computation is exactly the same as the second derivative computations that we were encountering earlier. It's now we're just throwing everything into a matrix. Now it's also safe to realize that this and this should be the same, that this and this should be the same, and then that this and this should be the same. It's going to save you a little bit of computational time if you wanted to. Anyway, I'm not actually going to go through that work. You can see it here and pause it if you would like. We're going to stop there for today. Thanks for sticking with me. Next section's on Taylor series. Maybe my favorite of the semester. Looking forward to it. See you then. Bye.